Section 8 on the Algebra of Exponents. Operations on radicals. We learned previously that we can add the base of an exponent only if the basis and the exponent are the same. For example, x squared plus x squared equals 2x squared, and 3x squared plus 2x squared plus 4x equals 5x squared plus 4x. The same concept is carried over to radicals, since radicals are simply rational exponents. For example, let's say we have the square root of 5 plus 3 times the square root of 5. If the index of our radical in lowercase 2, meaning an exponent of 1/2, is the same, and the radicand in lowercase 5 are the same, we can simply add the number of roots together. We have the square root of 5 plus 3 times the square root of 5, which is equal to 4 square root of 5. If we want to subtract, we work in the very same way. 5 square root of 6 minus 3 square root of 6 equals 2 square root of 6. The concept is exactly the same as when we worked with the operations on exponents. Let's give a few examples of how this can be utilized with other properties we have learned. Number 1, 2 times the square root of 5 plus 7 times the square root of 20. Here we see that the radicands are different. However, the second radicand is a multiple of the first. So let's split them up and then we can add them together. 2 square root of 5 plus 7 square root of 5 times 4. We know the square root of 4 is 2, and 2 times 7 is 14. So this simplifies to 2 times the square root of 5 plus 14 square root of 5, which becomes 16 square root 5. We were able to separate the square root of 20 into two parts, one that can be combined with the first term, and the second that was a perfect square. Number 2, 5 times the square root of 40 minus 12 times the square root of 10. We can use the same strategy here as the last example, but with subtraction this time. We have 5 times the square root of 4 times 10 minus 12 times the square root of 10. We know the square root of 4 is equal to 2. 2 times 5 is 10. So we have 10 times the square root of 10 minus 12 square root of 10, which equals -2 times the square root of 10. Number 3, the square root of x cubed plus the square root of y squared. Unfortunately, many times you won't be able to combine terms of radicals. Here is a square of a cube and a square of a square. At most, all we can do here is simplify the square of a square, giving us the square root of x cubed plus the absolute value of y. For much of our time here in algebra, we will have rational numbers containing radicals. However, for an expression to be in simplest form, we usually do not want any radicals in the denominator. When such a case arises, we use a special technique called rationalizing the denominator. This is a process that gets rid of radicals in the denominator, moving them to the numerator. The best part is that it doesn't affect the value of the expression. How does this happen? We are going to utilize the identity property of multiplication. We know that any expression multiplied by 1 does not change the expression. We also know that any number, including radicals, divided by itself equals 1. We are going to use these two ideas to show how to rationalize the denominator. Say we have 1 divided by the square root of 4. We can see very quickly that this is equal to 1/2. But let's rationalize the denominator first and see what happens. In order to rationalize the denominator, we are going to multiply both the numerator and denominator by the radical that we want to get rid of. In this case, the square root of 4. This gives us 1 over the square root of 4 times the square root of 4 divided by the square root of 4, which equals the square root of 4 divided by the square root of 4 times the square root of 4. Remember, this is still equal to 1 over the square root of 4, because the square root of 4 divided by the square root of 4 still equals 1. However, let's do something unique. We are going to multiply the denominators together. Now remember that the radical system represents an exponent of 1/2. And if we have 2 halves, we end up with a whole. Therefore, the square root of 4 times the square root of 4, which you know is 4 to the 1/2 times 4 to the 1/2, becomes 4 to the 1/2 plus 1/2, which equals 4. We now have the square root of 4 divided by 4, because we know the square root of 4 times the square root of 4 is equal to 4. We can now simplify. The square root of 4 is equal to 2 divided by 4, which equals 1/2. Thus we have the same answer and show that rationalizing the denominator works and doesn't change the value of an expression. Now, many times this will be used with radicals that cannot be easily done. For example, a common rational number encountered in trigonometry is 1 over the square root of 2. If we were to rationalize this denominator, we'd end up with the square root of 2 over 2. Since the square root of 2 is not a principal root or a root that gives a whole number, we stop here. What happens when there are multiple terms in the denominator containing a radical? We rationalize the denominator by the conjugate of the denominator. The conjugate would be the opposite operation. For example, to rationalize 1 divided by 1 plus the square root of 2, identify the conjugate of the denominator, which is 1 minus the square root of 2. Remember, we want the opposite. The rest of the procedure is the same as rationalizing the denominator. We have 1 times 1 minus square root of 2 divided by 1 plus square root of 2 times 1 minus square root of 2. Now we are going to use a type of distribution that we'll explore in the future chapter. Keeping everything in groups, we have 1 minus the square root of 2 divided by 1 plus the square root of 2 times 1 minus the square root of 2. Using the distribution property, which if you don't recall, you multiply each term in each of the parts being multiplied. That's 1 times 1, 1 times negative square root of 2, square root of 2 times 1, square root of 2 times negative square root of 2. So we have 1 minus square root of 2 divided by 1 times 1 is 1, 1 times negative square root of 2 is negative square root of 2, square root of 2 times 1 is positive square root of 2, square root of 2 times negative square root of 2 equals negative 2. Our two middle terms cancel out, and we're left with 1 minus square root of 2 divided by 1 minus 2, which we can simplify as 1 minus square root of 2 divided by negative 1. We can continue simplifying. We have negative 1 minus square root of 2, or square root of 2 minus 1. The distributive property we used was a unique property often called FOIL, which stands for first, outer, inner, last. And we'll cover that in the future lesson when we cover polynomials. This may seem a bit excessive and unusual, but it will become second nature to use such operations as we progress through algebra. Let's see these operations in action with a few examples. Number 1, 3 divided by 2 times the square root of 6. We begin with multiplying the numerator and denominator by the radical in the denominator that we want to get rid of. Note that we can include the 2 or not. Either way, the answer will be the same. We have 3 over 2 square root of 6 times square root of 6 divided by square root of 6. We recall that the radicals in the denominator will clear out because 2 halves in the exponents yield 1. So we now have 3 square root of 6 divided by 12. The 3 divided by 12 simplifies to 1 over 4. So we have the square root of 6 divided by 4. Number 2, 5 times the square root of 2 divided by the square root of 10. We now have an example with a radical in both the numerator and denominator. We proceed in much the same way. Rationalizing the denominator gives us 5 times the square root of 2 times the square root of 10 divided by 10. The 5 divided by 10 simplifies to 1/2, and the square root of 2 times the square root of 10 simplifies to the square root of 20. So we have the square root of 20 divided by 2. Remember that the square root of 20 can be called the radical of two products. So we have the square root of 4 times 5 over 2. The square root of 4 is 2. The 2 and the 2 will cancel out, leaving us with the square root of 5. This example showed that sometimes the entire denominator can be eliminated, making the number much simpler. Number 3, 2 divided by 3 plus the square root of 5. We begin here by identifying the conjugate of the denominator, which we see as 3 minus the square root of 5, and then multiplying the numerator and denominator. So we have 2 times 3 minus the square root of 5 divided by 3 plus square root of 5 times 3 minus the square root of 5. Using distribution on the denominator, we have 2 times 3 minus square root of 5 divided by 9 minus 5, which becomes 2 times 3 minus the square root of 5 divided by 4. The reason we didn't distribute the numerator is because there was a factor of 2 in the denominator that we can use in simplification. We now have 3 minus the square root of 5 divided by 2. Number 4, the square root of 3 divided by 9 minus the square root of 7. This example, much like example 2, gives us a multi-term denominator with a radical in both the numerator and denominator. Identifying a conjugate and then multiplying the numerator and denominator by it gives us the square root of 3 times 9 plus the square root of 7 divided by 9 minus the square root of 7 times 9 plus the square root of 7. This gives us the square root of 3 times 9 plus the square root of 7 divided by 81 minus 7, which simplifies to the square root of 3 times 9 plus the square root of 7 divided by 74. Distributing the square root of 3 across the numerator won't have any effect of simplifying this expression anymore, so this is the final answer. Finally, what happens when a radical has a base whose exponent doesn't match the index, such as the cube root of x squared? These numbers can be the trickiest to deal with sometimes. If you want, we can change the radical to exponential form, giving us a different look at our number. Remember that a cube root gives us an exponent of 1/3. So this radical is equal to x squared to the 1/3 power. Using the power rule, this becomes x to the 2 over 3 power. When we see our number in exponential form, we can see how much easier this was back in radical form. For a quick definition of numbers of this type, we see that the nth root of b to the m equals b to the m to the 1 over n power, which equals b to the 1 over n power to the m power, which equals b to the m over n power for all m and n in all, or as an element in all real numbers. Notice that this definition says that we can choose to work with the exponent first or the radical first. This is what we will utilize to make these types of numbers workable. While we won't see exponential numbers like this often in algebra, we will see them constantly in calculus. So it's best to get familiar with them now while we learn the basics with a few examples. Number 1, 4 to the 3 over 2 power. Beginning in exponential form, we can refer back to the definition to determine whether we want to take the square root or the cube of the number first. Since we already know the square root of 4, we'll start there. Rewriting the number gives us the square root of 4 cubed, which equals the square root of 4 cubed. Notice that this equality that I've written is the same as the one in the definition, just in radical form instead. Taking the square of 4 leaves us with 2 cubed, which equals 8. If I were to take the cube of 4 first, we'd have the square root of 64, which equals 8. Number 2, the cube root of 2 plus the cube root of 16. This can be where we get confused and make simple mistakes. It's tempting to go ahead and just write the answer as the cube root of 18, but that's wrong. We can only add the radicals together if both the index and the basis are the same. Therefore, we need to try to get the basis the same. First, we'll factor the second term, giving us the cube root of 2 plus the cube root of 2 times 8. We know the cube root of 8 is 2. So we end up with the cube root of 2 plus 2 times the cube root of 2, which equals 3 times the cube root of 2. This was our final lesson on exponents. I took this extremely slow because exponents are so prevalent and important to all of mathematics. Also, having a poor understanding of the algebra of exponents is often at fault of causing students to fail at calculus. Chapter 3 will be shorter, covering polynomials and operations on them.